In the Indian Ocean, at a water depth of 1,400 meters on the continental margin of Pakistan, countless white crabs are carousing on a mussel bed. How can life exist in such abundance at these depths, so far removed from any trace of sunlight? The answer has something to do with the small gas bubbles rising from between the mussels. The gas escaping from the sea floor is methane. Bacteria use it as an energy source and thus create a foundation for higher life forms in these deep-sea biotopes. But why is methane seeping out of the sea floor here? A white substance that can be seen at several places on the seabed provides a clue. This material is called methane hydrate. Under certain pressure and temperature conditions, gas molecules such as methane can crystallize with water molecules to an ice-like structure, so-called methane hydrates. In the ocean, pressure increases with depth. The phase boundaries shown in the diagram delineate the theoretical pressure and the temperature limits under which methane hydrate should be stable. The water temperature in the ocean decreases with depth, in this case to about 4 degrees Celsius at the seafloor. Within the sediments, however, the temperature rises again due to the geothermal gradient. So methane hydrates can only form within the hydrate stability zone, which is delineated by the phase boundaries and the actual temperature distribution. But of course, methane also has to be present. Methane is produced in all marine sediments from dead organisms, and because of its low density, it rises up to the methane hydrate stability zone, where it solidifies. If the pressure and temperature conditions change, then the hydrate becomes unstable, methane separates from the water again and seeps out of the sediment in the form of bubbles. Gas hydrates are stable under the sea floor at water depths greater than around 300 meters. That is why they are most commonly found on continental slopes and in the deep sea. Seismic investigations and drilling cores have revealed an extensive worldwide distribution of methane hydrates, which also underlines their importance. At the Marum Institute in Bremen, scientists are working toward a better understanding of the role of methane hydrates for the deep-sea ecosystems, the global carbon cycle, and the stability of continental slopes. The hydrates retrieved from the seafloor are stored in special containers, deep-cooled in liquid nitrogen to maintain their stability. This piece clearly shows how the white methane hydrate and the brownish sediments combine to stabilize the seafloor. Methane hydrates have received special attention because the energy stored in them may be used by people in the future. If we compare the amount of carbon stored in the form of oil, natural gas and coal with that in the form of methane hydrates buried under the seafloor, then we have to consider that methane hydrates could represent a possible energy source for the future. There are, however, a lot of other questions that will have to be answered before it is possible to commercially retrieve the methane hydrates.